Hello everyone. We are from EC Department, Tyagarajar College of Engineering, Madurai. We are here to explain the research paper titled Analytical Modeling of Flicker Noise in Halo Implanted MOSFETs. We are team Indus and the team members are Stanley Jones, Om Prakash and myself Adi Vithinathan. Introduction. This paper presents an improved analytical model for flicker noise in MOSFETs. The proposed model captures the effect of high trap density in halo regions of the device, leading to different bias dependence of flicker noise. This model is more compact than existing models and is compatible with BSIM6, that is the Berkeley short channel IGFET model, the latest industry standard model for bulk MOSFETs. The model is validated with measurements from the 45 nanometer low power CMOS technology node. This work is supported in part by the DST Fast Track Scheme for Young Scientists, Ramanujan Fellowship, the Indian Institute of Technology, Kanpur Initiation Grant, and Semiconductor Research Corporation. For low power technology, strong halo implants are necessary to suppress parasitic 2D electrostatics for minimum length devices. Strong halo implants are needed, but they can be detrimental to analog performance. In addition, existing models cannot capture the behavior of halo implanted devices. This paper discusses the physical mechanism of halo implanted devices and presents an analytical model to capture the behavior across length, considering both non-uniform threshold voltage and increased trap density. Important definitions. Let us see about flicker noise. Flicker noise, also known as 1 by F noise, is a type of electric noise characteristic by its frequency dependence. It is more prominent at low frequencies and decreases as frequency increases. Flicker noise is a common phenomenon in electronic devices and can affect their performance, especially at low frequencies. Next, we see about compact model. A compact model is a simplified mathematical representation of electrical behavior of a semiconductor device, such as a transistor. It is used in circuit simulations to predict device performance and interactions in complex integrated circuits without the need for detailed physical simulations. Now we see about BSIM6. BSIM6 is a Berkeley short channel IGFET Model 6, a compact transistor model developed at the University of California, Berkeley, used to simulate and characterize MOSFET behavior in IC designs. It provides equations for MOSFET electrical characteristics and addressing short channel effect in advanced semiconductor technologies. And next we see about halo doping. Halo doping is a semiconductor manufacturing technique used to modify the electrical properties of regions surrounding a MOSFET. By introducing specific dopants, it helps control short channel effects and improve device performance and reliability. Halo MOSFETs have a specific characteristic. Let us check them using the graph shown here. Drain current, flicker noise power, spectral density versus drain current at VDS equal 0.55 volt, both normalized to the channel width. Measurements are from the same technology and shown complex dependency on gate voltage, especially for long channel device. Weak inversion noise is dominated by contributions from halo regions and therefore there is no impact of length scaling on 1 by F noise.
Now, let us see about the design. The presented formulation is based on small signal approach, which is similar to the impedance field method. In a very crude form, Overall drain current noise SID can be expressed as the following equation, where SID is the overall drain current noise, RH is the equivalent resistance, RCH is the resistance of length L minus LH. This can be implemented by simple two-transistor subcircuit model, where resistances of channel and halo regions are calculated by SPICE software. However, such an implementation cannot be used for a practical industry standard compact model formulation since it degrades the simulation speed as well as complicates model parameter extraction procedure. Here, we will present a complete analytical model that can successfully reproduce the series transistor noise behavior without the above limitations. There are two images here which tells us the small signal analysis of two transistor noise circuit. The principle of superposition is used to obtain total noise from individual noise contributions. The first image is noisy halo transistor and noiseless channel transistor, and the second image shows the noisy channel transistor and the noiseless halo transistor. Now, let us see the methodology implemented in this design. The model is validated with the measurements at 45 nanometer CMOS technology. Validation is carried for both long channel as well as short channel devices at BDS equal to 0.55 volt. The given image shows the design for this methodology, where the total length L is segmented into two parts, a region of higher doping of length LH with equivalent resistance RH, noise PSD SIDH, and another low doped region of length L minus LH with resistance RCH and noise PSD SIDCH. Unlike the short channel case, long channel device shows significant bias dependency and the model is able to accurately reproduce the experimental characteristics both for the long and short channel devices. For the better understanding, long channel noise PSD along with the halo and channel transistor PSD is shown in the above figure. Now, let us use the parameters and derive an equation. Using small signal analysis, we get equations 2 and 3, where GMCH and GDCH are the transconductance and output conductance of channel transistor, and GDH is the transconductance of the halo transistor. Similarly, the noise PSD due to the channel transistor is given by equations 4 and 5. The total drain current noise PSD becomes SID equals SID1 plus SID2, which gets us to equation 8, which is SIDH into CFH plus SIDCH into CFCH. Looking at equations 9, 10 and 11, we refer to the multiplying factors to SIDH and SIDCH in 7 as contributing factors CF, where NQ, mu, Cox and Vt are the slope factor, effective mobility, oxide capacitance per unit area and thermal voltage respectively. QSCH, QDCH, QSH and QDH are the normalized inversion charge densities at the source and drain ends of channel and halo transistor respectively. QSH and QDCH are obtained from analytical solution of BSIM6 charge equation given by equation 12, where pinch off potential is given by equation 13 and is calculated independently for the two transistors using source potential VCH equals Vs and VCH equals Vd respectively. Vg, VFB, phi f and gamma in these equations are the normalized gate voltage, flat band voltage, bulk potential and body factor respectively, and psi p naught is the approximation of pinch off potential when it is close to 0. To calculate QDH and QSCH, the fact that the same current flows in one transistor and 2 transistor noise equivalent configuration is used. This gives us equation 14 and 15, where IH and ICH are the normalized drain current of halo and channel transistor respectively. Since IDS is known from DC modeling, the previous equations are solved for equation 16 and 17. Here we have used the unified model for halo and channel transistors separately, where SID is expressed as equations 18 and 19. It is important to note that SIDH and SIDCH are in explicit form, since equations 18 and 19 can be expressed as a function of QSH, QDH and QSCH and QDCH respectively. Also, note that SID in the halo region might be locally higher than in the channel region due to increased trap density, which is captured by the noise parameters of the halo transistor. Hence, formulation of SID is based on the local trap density, inversion charge densities specific to the region that generates the noise as well as the length of the region. Using equation 18 and substituting 16, 17, QSH, QDCH in 7 gives the overall PSD.
So let's see the results and discussion. The model is validated with the measurements at 45 nanometer CMOS technology. Validation is carried for both long and short channel device at VDS equal to 0.55 volt. Unlike for the short channel case, long channel device has significant bias dependency and the model is able to accurately reproduce the experimental characteristics both for the long and short channel devices. Due to higher doping in halo MOSFET, it has higher threshold voltage than the channel counterpart, which leads to significantly lower inversion charge density, especially at low gate voltages. For a given current, SID is inversely proportional to the square of inversion charge density and therefore halo transistor will have much higher SID compared to the channel transistor. Furthermore, in weak inversion, GD, H much more less than the GM, CH, as QS, CH much more greater than the GD, H, since halo transistor has higher threshold voltage leading to CFH equal to GM, CH plus GD, CH divided by GM, CH plus GD, CH plus GD, H approximately equal to 1 and then CFCH equal to GD, H divided by GM, CH plus GD, CH plus GD, H approximately equal to 0. Since the contributed noise is the product of CF and SID, overall noise is dominated by halo transistor noise in weak inversion, that is SID approximately equal to SID, H. So this is the graph of model validation with the long channel device, that is SID versus IDS at VDS equal to 0.55 voltage. So this graph shows that SID asymptotically follows halo transistor noise in weak inversion and channel transistor noise in strong inversion. And this is the graph of contribution factor of halo and channel transistors versus drain current. Here the graph shows that in weak inversion, CFH much more greater than the CFCH and thus SID is dominated by the noise from the halo region. On the other hand, CFH falls rapidly in the strong inversion leading to the negligible contribution from halo region in SID. The role of CF in this model is similar to that of impedance field, which is responsible for noise propagation from a point in the channel to the drain terminal. And this is the graph of simulated drain current noise spectral density versus drain current for constant gate voltage and varying VDS from 0.1 voltage to 1 voltage for the long channel device VGS equal to 0.25 voltage. Here the graph shows that halo regions offers much higher resistance than the channel part due to its high threshold voltage and hence the total noise is determined by the noise of the halo transistor. And this is the graph of simulated drain current noise spectral density versus drain current for constant gate voltage and varying VDS from 0.1 voltage to 1 voltage for the long channel device VGS equal to 1 voltage. Here the graph shows that high gate voltage strongly inverts both the halo and channel regions. However, resistance of the channel region is larger as its length is large compared to the halo region. As a result, total noise is dominated by the channel region noise. Let's see the conclusion of this paper. An analytical model of flicker noise for halo implanted MOSFET is presented, and the impact of halo regions associated with the device on flicker noise is modeled using a separate MOSFET connected in series with the channel transistor. And the model is a significant improvement over existing models in capturing bias and channel length dependencies of noise in device employing strong halo technology. This model is amenable to be integrated with BSIM6 and provides an excellent solution to model the 1/f noise for the low power CMOS technology with high quality analog capability. Thank you.